Optical interferometry has revolutionized astronomy in recent years, but it's also one of the most misunderstood topics, especially here on YouTube. For example, the leading educational video on this topic describes the Keck interferometer as simply combining the images of two telescopes using a computer to act as an 85-meter telescope, which is a vast oversimplification. We also have a video from Tom Scott where he visited the Very Large Telescope Interferometer, and I think this is a really great video overall, but at the end of the video he comes to the conclusion that we will never build a telescope larger than the Extremely Large Telescope because we will be replacing them with interferometers. And I also think this is a faulty conclusion. And so in today's video, I'm going to give you the full technical understanding of optical interferometry and interferometry overall. And then I think you will better understand why these arguments are flawed, and you will just have a better appreciation of astronomy overall. The key difference between direct imaging is that in interferometry, we are actually directly recording interference patterns of light called fringes instead of an image that a camera would normally collect. Images for telescopes are formed when light from a mirror is focused onto a focal plane in 2 dimensions, and millions of pixels will record the intensity of the light. For an interferometer, however, the entire field of view will be a single airy disk, roughly equivalent to a single pixel on a telescope's focal plane. And once the interference pattern or the fringe is created, we will be recording the complex visibility, which is the visibility of the fringe and the phase of the fringe, and that's going to record spatial frequency information about our target. Okay, but it's not going to form an image, at least not in a single point in time. And so the inherent trade-off between a telescope and an interferometer is, for a telescope, it has good quality of image and field of view, but for an interferometer, we can sacrifice those qualities for a very, very high angular resolution. The idea for both optical and radio interferometry has its origins in the dual slit experiment, originally done in 1801. When you form an interference pattern for a point source, this will have perfect peaks and valleys of constructive and destructive interference. When you have an extended source, however, the interference pattern will start to blur. And so in this way, this can describe angular frequency information about your target at a sub-pixel level. The orientation of your baseline, or the 2 telescopes that you're using, will determine the axis of the target that you're recording the information about, and then also the distance between the 2 telescopes will set the angular frequency of the target that you're going to be recording, because this is also setting the resolution. And so that distance between the 2 telescopes is called the baseline in interferometry, and the effective resolution is set as the wavelength of light divided by twice the baseline. And this is very similar to the resolution of telescopes, which is roughly the wavelength of light divided by the diameter of the aperture. For an interferometer, it's going to be a tiny field of view of a single airy disk, and for a telescope, you're going to be forming an image using that entire collecting area of the mirror. Another point to make is that interferometry is typically used for very bright sources in the optical range, because if you wanted to make a telescope with the equivalent resolution, it would be collecting a large amount of light, but for an interferometer, you're only collecting a tiny fraction of this, and so your signal to noise ratio is going to be much lower, even after all of the corrective actions that we take. And with a single baseline, it's not possible to form an image at any given point in time. However, when you have many different baselines with many different orientations and frequencies, then we can start to form an image. And so for you to understand this, I'm going to give you a short background on the math of Fourier transforms and Fourier analysis. So the point of a Fourier transform is to convert back and forth between the spatial domain, or the domain of pixels of an image, and the frequency domain, or the Fourier domain, that we see in fringes. And it does this in practice by taking a signal and applying many filters to that signal over a range of different frequencies. You'll also notice the imaginary term in the Fourier transform, and this is because in the Fourier space, the values are complex, meaning you have a real value and an imaginary value. Okay, and this is sort of an artifact of this kind of signal processing within electrical engineering, which is when this is typically used. So for images, we convert from the spatial domain to the frequency domain, and for signals, and even like radio signals, we're converting from the temporal domain into the frequency domain with Fourier transforms. And one more thing, we have the inverse Fourier transform, which basically does the exact same thing, except it's filtering from the frequency domain and then moving it back into the spatial or temporal domains. Okay, so we're going to go through this demo really quickly to explain how the images are going to be created in the pixel domain and then a spatial domain from the frequency domain data that we record. So we can see here I have this demo. In this first part of it, we have these different images and they're converted into the frequency domain using a Fourier transform. Now in this first image, you can see it's very low frequency features with these stripes. There's only about 4 of them. And so in the frequency domain, this is going to be represented with these 2 little dots at a very low frequency. So they're very close to the center, which is 0, 0, representing the lowest frequencies. Now in this domain, these 2 dots are going to be complex values, so they'll have a real value and an imaginary value. And so it's usually represented as the magnitude and the phase. So the phase is like the angle between the real and imaginary values or axes. Okay, so next we have a higher frequency. Okay, so these 2 dots are going to be further away from the origin because the frequencies are higher. And since the frequencies are higher, the stripes are much faster. Now you'll notice that these dots are horizontal. If you make the dots vertical in that domain, then the features that are going to be represented, the angular frequencies, are going to change direction. Okay, so now we have a very low frequency, but we have a different direction, and then we have the low frequency stripes. Okay, same thing here. We have higher frequencies in that direction, and we get a very high frequency stripe pattern, as you can see there. Now it's the same sort of thing. If we want to make a checkerboard, we could do low frequency stripes in both directions, and we get this sort of blurry low frequency checkerboard pattern. If we want to do a higher frequency, we do the same thing, where you can see the dots are at higher frequencies, okay, in both directions. Now here's what it looks like when you have a complex image, or a complicated image, I should say. And here we're using the Mona Lisa, and you can see that the frequencies, there's a bunch of different frequencies that are needed to generate this in the Fourier domain. And so if you want to actually reconstruct an image properly, you're going to need a lot of different frequencies. Now here's an example of what happens if you only use certain frequencies. So here we have some filters. This is called a low-pass filter. So a low-pass filter, you're basically just using the central cross section. You're only retaining these values because those are the low frequency data points. And you can see it's basically a blurring effect. It looks like sort of diffraction. You can't see those high frequency features. Now a high pass filter is when you just take these edges, you only take the very high frequency values, and you can see it's just the fine details, but you can't actually resolve what you're looking at very well. When you're building an interferometer, here's just a sort of idealized one that I've created. Every single baseline in between the different telescopes is going to represent a different point in that Fourier domain or that frequency domain. Each of those will have a complex visibility that will be measured. And this is called filling in the UV plane because we want to get as many of those points in Fourier space as possible. Now, one strategy that they use to get more points, actually there's a few strategies they use. The first one is that they use the rotation of the Earth. So if you're taking observations over an entire night, the orientation of that baseline is going to change over the course of the night, especially if something is out of plane from the equator of the Earth, okay, your target that you're looking at. You can also have certain baselines, for example, auxiliary telescopes on the Very Large Telescope Interferometer. You can actually move where the telescopes are relative to one another. Okay, so you actually move the telescopes. Okay, the other strategy basically only works for radio telescopes, but this is going to be to record the observations at 2 telescopes very far away from each other, and then you will digitally combine and digitally create the interference pattern later on. And so this is how you make telescopes sort of the size of the Earth, like the Event Horizon Telescope. Okay, and then one more technique that they use is the reason a baseline will set a certain point in the Fourier plane is because the length of the baseline determines the resolution. Okay, but the resolution also depends on the wavelength of the light. And so if you use a bunch of different wavelengths of light using the same baseline, you can get a range of different angular frequencies, meaning a range of different resolutions, and so you can fill in more space. Okay, so moving on from filling in the UV plane, something I've done here, I set out this very dense array. Okay, again, this is just a simulation, it's sort of ideal. That's only 400 meters across, but I use a ton of different points. Okay, and then here I make one that's 5,000 meters across. Okay, so more spread out. And then I make one that's combined together. Okay, and you can see here it fills in these low frequencies towards the center of that Fourier plane very well. And here we have some higher frequencies that are filled in better. And here's the sort of ideal situation. And what you can see, all we're doing here is inverse Fourier transform of this data back into the pixel space or the spatial domain. It's called a dirty image because usually when they do this initial processing, because of the turbulence in the air, it basically looks pretty poor for optical interferometry. But anyway, you can see when we have these low frequency samples, the image is sort of hard to resolve, and you can basically mostly are just seeing the low frequency features. In this one, where we have very spaced out telescopes, it looks like a high pass filter. We're just getting those very high frequency features, and we still can't really see what's going on. It's only when we use this combined antenna layout that we get this perfect dirty image that you can see here. This is super idealized for optical interferometry, and the best optical interferometers we have today only use 4 to 6 telescopes, again, over the course of a night, or over the course of a period of time where they can use the rotation of the Earth. But still, the dirty images that get produced will almost never look this clear, okay, especially because we're imaging very distant, typically stars or galactic sorts of objects. Okay, so getting back on topic, the idea for astronomical interferometry was originally invented in 1868, and the idea was to use the interference patterns of 2 telescopes to measure the sizes of stars. This had some very limited success early on, but in 1891 it was successfully used to measure the sizes of Jupiter's moons. In 1921 they had this breakthrough where they were able to image Betelgeuse, and so Betelgeuse is a red supergiant star, meaning it's very wide and also very bright, and so it's perfect for this kind of interferometry. And they were able to resolve it at 47 milliarc seconds, which is a very fine resolution. And if you don't know an arc second, an arc minute is 1/60th of a degree, and an arc second is 1/60th of an arc minute, and so on and so on. Now at the time, they were limited to some pretty primitive optics and computer processing, and they were just limited to 2 telescopes for the most part, and so they're not able to form the type of images that we see with interferometry today. A lot of focus shifted towards radio interferometry, although it did improve slowly, especially in the 1970s and 1980s, and then it really had a giant leap in performance within the last 20 years. But for now, let's briefly discuss radio interferometry. So any single radio telescope will actually have very low angular resolution, and this is because of the wavelength of light that we're using. We're using a very low frequency, and like I described earlier, the resolution is going to be set by that frequency for a typical telescope. So even the 300 meter wide Arecibo telescope, in fact, only had the same resolution as a 1 millimeter optical mirror. And so because of this, a lot of the largest and best performing radio telescopes are actually radio interferometers. And the reason for this is that in radio interferometry, we can essentially make the baseline, or the distance between the 2 telescopes, as far apart as we want. This is because we can simultaneously and coherently convert that analog radio signal into a digital phase history using an analog to digital converter. And we can then take those digital signals and interfere them later in a supercomputer to produce the interference pattern. The interference caused by the atmosphere is also usually correctable at these lower wavelengths, and the frequency is well below the limit that modern electronics can sample at the Nyquist frequency. And so the Nyquist frequency basically just means that if you want to record the phase of a signal, you need to sample at twice the frequency of the signal you're recording. And so because our best computers typically run in the gigahertz range, and optical light is on the order of terahertz, it's basically impossible to convert that analog signal into digital. Okay, but for radio, it's basically a very simple process, and we do it all the time. But this technique is how we created the Event Horizon telescopes to image the surrounding area of a black hole in radio. And they were able to do this by recording at the same time the output of the telescopes pointed towards the black holes, and then they actually took the hard drives of those digital signals and then brought them to a central computer from all around the world, and they were able to produce those interferometric images. Okay, and they also used a bunch of different modeling techniques for that. But the takeaway there is that they're able to create angular resolutions down to 19 micro arc seconds because the baseline was nearly the size of the entire Earth. And so that's really impressive because even our best optical telescopes, even the very large telescope interferometer, has resolutions close to 1 milliarc second, and imaging telescopes usually are in the single digits or double digits of milliarc seconds. We don't have this luxury for optical interferometry. So for optical light, either visible or infrared, it's going to have a wavelength of about 1 micron or smaller. And so this is going to oscillate at a rate in the hundreds of terahertz. Okay, so this is not possible to pass through a normal analog to digital converter. Instead, we actually have to physically interfere the light, and this does pose some challenges. The first one is, depending on the type of beam combiner you use, with every additional telescope that you add, that will produce non-linearly more baselines, and so you'll need to split the light into more and more different fringes. And depending on the beam combiner, this can make the fringes much dimmer and decrease your signal to noise ratio. And this is one reason why even our best modern optical interferometers have only 4 to 6 telescopes, whereas the VLA and ALMA arrays, which are some top-tier radio telescope interferometers, have 27 and 66 radio telescopes respectively. And the next challenge is creating a stable interference pattern. And this is actually much more difficult for optical light. So like I said, when the wavelengths can be on the order of 1 micron, you're going to have disturbances in the atmosphere that are also the size of around 1 micron or even larger in some cases. And you also just have vibrations within your telescope. You'll need to correct for those to make sure that the distance the light is traveling is stable, and so that those interference fringes will be stable and you can actually record the phase for them. But because of this problem, this limits the length of the baseline that you can use because it gets much more difficult with the more telescopes you use and the larger the baseline. And so for this reason, the largest optical interferometer baseline is 330 meters and has actually recently upgraded to 550 meters. Okay, but still minuscule compared to the size of the Event Horizon telescope, which again, almost the size of the entire Earth. Okay, but despite all these different challenges, we also have the benefit of having that much higher frequency and much smaller wavelengths, which increases the resolution significantly. So these optical interferometers have still been able to make some really important discoveries that the radio telescopes have not been able to accomplish. The most powerful interferometer, optical interferometer that we'll talk about today, is the Very Large Telescope Interferometer. And so this one has 4 telescopes of 8 meters across. It's also just one of the largest telescopes in general. And it also has these auxiliary telescopes where you can move them, create different baseline lengths. Okay, we also have CHARA and the Navy Precision Optical Interferometer. Those are some very large arrays. And then we also have the Keck Interferometer, which is actually closed. Okay, but the Keck Interferometer is one of the largest optical telescopes. There's 2 of them, and they used to be able to create interference patterns with it. And then we have the large binocular telescope interferometer that's shown there as well. So modern interferometers do not interfere the light in the same way as the original dual slit experiment. Instead, they use beam combiners from 2 different telescopes that are physically separated by that baseline distance. Some beam combiners are called pairwise, meaning they only combine 2 different beams from 2 different telescopes. There are others called all-in-one combiners that will combine the light from several different telescopes, and then it will produce multiple different fringes on the same measurement focal plane. Now, to measure the phase of the fringe pattern, because it's a complex value that we need to measure, we actually need to measure the quadrature phase, which means we need to measure the visibility at 4 different phase offsets. And so some beam combiners will actually split the beam into 4 different phase offsets, and then some interferometers instead temporally change the phase, so they'll just change the distance that the light travels over time to get that complex measurement. So I said this earlier, but for the pairwise beam combiners, the problem is that the number of baselines will scale as n times n minus 1, where n is the number of telescopes. And so if you're using pairwise combiners, the fringes are going to become more dim with the more telescopes you add. Okay, now in these modern systems, they will be using adaptive optics within each of the telescopes. And so before the light even gets to the interferometer, it will go through its own adaptive optics, which is going to try to remove the effects of the atmosphere from the wavefront of the light that gets sent to the interferometer. Okay, and the way they do this is they use a guide star, so that might be an actual star, or it could be an artificial star created with a laser, and they will look at the image, and then they'll have a closed loop control system to adapt this and try to make that star appear more like a single point for that point spread function. Okay, and that will sort of remove the aberrations. Okay, but once they've done this, there will still be remaining aberrations caused by the atmosphere that need to be corrected. And so they have another layer of adaptive optics that's only focusing on the fringes. And so we want to stabilize the fringe. And so this can be a separate fringe from a very bright star, or it can be from the target itself. But this will actually be passed into another layer of adaptive control that the system can make tiny adjustments to the length of that the light travels, like we saw in the Tom Scott video. They have these tiny little piezo actuators that can change the length of that by microns or nanometers, and then that is aiming to stabilize our fringes. And once you have stable fringes, you can make measurements over several seconds or even minutes, and then that will improve the quality of those complex visibilities significantly. Another point is that the fringe doesn't just need to be stable. The other thing we need is for the light from the different telescopes to travel the exact same distance. And the reason this is needed is that we need the light to be coherent, or the phase difference to be zero, for all the different wavelengths. Okay, so if we don't do this, then because the different wavelengths change phase at different rates, if we don't make the distance the same, then they'll be out of phase with each other. Okay, so in order to get coherent measurements, the distance needs to be exactly the same, and this is why we have delay lines within the modern optical interferometers. And so that distance of the delay, that will need to change based on the distance to the target and the orientation to the target of the two telescopes. And so they have these underground delay lines where they can move these mirrors on carts to very accurately change that distance, and then also make those very small adaptive changes too. And this was shown in the Tom Scott video at the Very Large Telescope Interferometer, but with those delay lines, they're actually able to stabilize that distance to within something like 130 nanometers, which is really impressive. Now, for optical interferometers, even with all of these adjustments, the phase of the fringe is still too corrupted by the atmosphere to produce clear images without some corrections in the image processing. And one way we clear this up is with this concept of closure phase. So closure phase is an observable quantity for a combination of three different baselines that form a triangle. And the math works out where the term for the atmospheric instabilities is canceled out for closure phase. And the reason for this is basically that for, say, telescope A, that forms baselines 1 and 2, it will have that same interference and that same jitter on both of those baselines, but baseline 3 will be free from that effect. Okay, and the same thing is true for the other two telescopes. And for this reason, that term is able to cancel out just for closure phase. And the number of closure phases that we have will increase with the number of telescopes, sort of non-linearly. And this is because you need 3 telescopes to form a single closure phase. Okay, so when you have 4 to 6 telescopes, this is somewhat better in that respect. But anyway, the point of closure phase is that some techniques to process images will use a modeling approach. And so what this means is that they have these visibilities, and then they also have the closure phase, and they then use a model to test out a bunch of different images, and then it's going to optimize and try to find the image that best fits those parameters. Okay, so if it best fits the closure phases and the complex visibilities, then this is the best estimate for the object that's producing these fringes in our results. However, we do have a more basic approach to image processing, and this was first introduced in 1974, and it's called the clean method. Okay, and so this was originally used for radio interferometry. So the way that clean works is we go through and apply the Fourier transform, like I showed in the demo, that will produce the dirty image. Okay, but the problem here is that it will still have these side lobe effects, because again, we're not including the full length of the baseline with a light collecting area. Okay, so it has these side lobes. And the way that this is corrected is with a deconvolution. And like I said, in the more modern times, we have these modeling approaches. So we have something called the maximum entropy method, which was first introduced in 1984. But then now there's a whole field of different optimizations for all these different modeling approaches. And they all have basically different approaches for every single type of source. So they'll have some for binary stars, some for galaxies, some for black holes, things like this. There's a whole field just for modeling of interferometry. So there are many more nuances and whole fields of research within optical interferometry, but I think you should have a pretty good understanding of how it works now. And so to end things, I'm just going to show off a few different discoveries and observations that we made within the last 10 years with optical interferometry that are really impressive. Okay, so for this section, I'm just going to briefly walk you through this part of this review paper that's showing you the advances in optical interferometry in the recent past. So you can see here, here's the magnitude. So this represents how bright stars are. And you can see there's been this huge jump just in the last few years with this most advanced instrument called gravity that they added at the Very Large Telescope Interferometer. Okay, and so that's able to image much dimmer objects. And the reason for this is that it's able to make much more stable fringes. And then it says here they can do greater than 50 seconds of exposure times or coherent integrations instead of 50 milliseconds. What you get for the most part with interferometry is just a very, very good angular resolution. And so for the most part in astronomy, a star is usually going to look like a point source. It's usually going to be maybe a single pixel. It's going to be within the fraction limit. But with interferometry, you can actually see you're able to resolve features of these stars. Okay, so especially with these large red giant stars, you're able to see sunspots and things like that. And then you can also see sort of temperature differences in these rotating stars. A lot of interesting discoveries there. Okay, we're also able to see the disks forming around these new stars. Also, some really interesting things with the black hole. Obviously, the radio interferometry has even higher angular resolution, so it's able to image, the surrounding area of the black hole itself in radio. Okay, optical interferometry has not gotten that good yet, but what we can do is image all of these stars that are around the black hole at the center of the galaxy. Okay, so here they're talking about how they measured the orbit of the S2 star, and I actually talked about this star on one of my other videos where I was discussing how hard it would be to actually leave the galaxy as far as like humans or robots or whatever. Okay, and then finally we have some more stuff about active galactic nuclei. They're actually able to test some of Einstein's relativity and some other theories about black holes based on some of these observations as well. So you can see it's really important to astronomy. Oh, and here you go, even exoplanets. Exoplanets you need a really good resolution for, and then you need to do spectroscopy on them. So that's a really challenging thing to do, but of course, this is something that interferometry can somewhat handle. Obviously, you can't do surveys. There's a lot of stuff in astronomy. I'm not an expert in astronomy, but there's a lot of stuff that an interferometer cannot do. So it's really not a magic bullet, but it is definitely super important. So you can see optical interferometry is a really impressive and promising technology that will continue to improve, and it's really able to produce some good science, especially for those really bright objects. But you will notice that optical interferometry is not making all of the discoveries within astronomy, and most astronomy still needs to use normal telescopes, and a lot of telescopes need to have a very wide field of view to conduct surveys of the entire sky or large portions of the sky, or just to collect more light to have a higher signal noise ratio for dim objects and things like that. Okay, so there's really these inherent trade-offs. Okay, like I said towards the start of the video, and I hope that kind of clears up some of those misconceptions. And so this idea that the extreme large telescope will be the largest telescope ever, you can see why that doesn't really make sense. So in the future, I think we will have continually larger and larger normal imaging telescopes and also larger interferometers. And the future of interferometers is especially exciting because you'll notice a common theme in all of those problems with optical interferometry I was discussing. Probably 90 to 95% of it is just the fact of the turbulent atmosphere of Earth. And so if you can simply put an interferometer into space, that allows you to make a much larger baseline and have many more telescopes. And there's a project for this called LIFE that's in the planning phase. And here the idea is to have a formation flying satellites, and where each of them is optical telescopes, and then they beam their image onto a central satellite to combine the images and make the interference patterns. Now, I'm not sure if this one will work exactly, but I think this is definitely the future, and even maybe just something like if you took the very large telescope and put it on the moon, for example, you could have some really strong performance. But eventually, you can imagine with optical interferometry, once we can make baselines that are the size of the Earth or even larger, like in the Event Horizon telescope, this is going to allow us to see some incredibly detailed things and really make some great discoveries. So I think maybe centuries into the future, this is a really promising technology. But anyway, that's going to wrap it up for me. I hope you enjoyed this video about optical interferometry. If you did, make sure to like and subscribe and share this with your friends. I'm also going to leave some links in the description. So a lot of those images that I showed throughout this video come from this review paper. And so I'll link that. I'll also link the European Southern Observatory website. They have some interesting stuff there. There are also a lot of textbooks on this area. They're all kind of expensive, so I ended up not buying any of them, but you might want to do that if you're interested in the topic. Anyway, with that being said, thanks so much for watching and have a great day.